Welcome everyone. I am Pabido Macmillan. Let's begin. Organic semiconductor in solar photovoltaic have contributed much for efficiency improvement. Introduction. Organic semiconductors are receiving increasing attention these days because they have many attractive properties, including lightweight, low cost production, low temperature processing, mechanical feasibility, and abundant availability. This distinguish them from their conventional inorganic counterparts. counterparts. The recent successful commercialization of active matrix organic light emitting diodes for high-end smartphone displays suggested that organic compounds have promising prop- prospects for use in various other electrical and optoelectric devices. For example, the fabrication for of solar cells, transistors, photodetectors, and lasers with organic semiconductor can be highly feasible and high efficiency. Another attractive property of organic semiconductor is that they can be processed using simple solution processing techniques. Example: inkjet printing, reel-to-reel fabrication, making the fabrication of electronic devices much easier and cheaper. As Professor Heger said in his Nobel lecture, I am convinced that we are on the verge of a revolution in plastic electronics. We foresee a rapid advance in the field of organic semiconductor, bringing increasingly more inexpensive, workable, and smart organic devices into our daily lives. Organic semiconductors. Organic semiconductors combining the attractive properties typical of plastics, solubility, mechanical strength, and adjustable physicochemical properties, and electrical conductivities typical of metal, enable the development of inorganic devices. However, the implementation of all possible applications of conductive macromolecules still require a great deal of advanced research and improvement in manufacturing technology. In fact, organic electronics and photonics is considered one of the most rapidly growing technology platforms based on the combination of novel nanomaterials and cost effective large area production processes. The potential application of these materials include organic light emitting diodes for displays and lighting applications, electronic paper, thin film batteries, supercapacitors, organic photovoltaics, sensor and biosensors. Some organic semiconductor devices have already been commercialized, although the performance and lifetime of devices are still limited. Among other advantages, organic semiconductors are easy to process and can be used to fabricate inexpensive devices. Materials: amorphous molecular films. Amorphous molecular films are produced by evaporated or spin coating. They have been investigated for device applications such as OLEDs, OFEDs, and OSs. Illustrative materials are tris, it, hydroquinonato aluminum, C, phenol C61, butyric acid methylate ECC, ester, ester, pentacin, carbonous, and pethano, phthalocene. Molecularly topped polymers. Molecularly topped polymers are prepared by spreading a film of electronically inert polymer. Example: polycarbonate topped with typically 30 of charge transporting molecules. On a base electrode, typical materials are the terpenoids. They have been investigated for use as photoreceptors in electrophotography. This requires film have a thickness of several micrometers that can be prepared using the doctor plate technique. Molecular crystal. In the early days of fundamental research into organic semiconductors, the prototypical materials were free-standing single crystal of the acin family. Example: anthracene and titrazine. The advantages of employing molecular crystal instead of amorphous film is that their charge carrier moleculities are much large. This is of particular advantage of OFET applications. Examples are thin films of crystalline rippers prepared by hot wall epitaxy. Optical transmissions in organic materials. When an organic molecule is subjected to light excitation, it may absorb a photon. The molecule, which is initially in the electron energy based state, then moves into a higher energy electron state, known as the exit state. By the absorption of a photon, an electron hole pair is generated. This process of absorption is efficient when the photon's energy is similar to the gap between the energy levels of the base state and the exit state. Such an excitation represents the passage of an electron from the base state to higher energy orbital. The quasi-particle formed by the electron and its environment is called a negative polar Columbian interaction between an electron of the LUMO and a hole of the HOMO leads to the formation of what is known as an exciton. Nanostructure of organic solar cells. X-ray based characterization. Organic semiconductors usually consist of light element such as carbon, hydrogen, and oxygen, leading to the weak signals of wide angle scattering. Therefore, the grazing indication techniques are employed to characterize the stacking structure of bland films, including molecular orientation and crystallinity. Grazing incident wide angle scattering can reduce the molecular stacking information. Example: each are on or face on based on the peak's position in the profiles. Further, the crystal size of organic semiconductors can also be achieved according to the Sketcher equation, which should identify the full width at half maximum of the scattering peaks. Small angle scattering techniques are usually employed to study the base separated morphology with the nano-sized scale. The construct of samples with small angle X-ray scattering comes from the various X-ray scattering abilities of blend materials due to their electron densities based on the position of the scattering peak. The base domain size can be interpreted after fitting the pristine data. Recently, resonant soft X-ray scattering has been developed to analyze the morphology of blend films due to the construct of RSO excess coming from the functional moieties of materials. There is a higher scattering intensity than that of the hard X-ray scattering technique. Therefore, it is a powerful tool to investigate the base domains with a length scale from several nanometers to several micrometers and identify the relative base domain purity of thin films in various process conditions. MA and co-workers reported quantified morphological characteristics in relation to photovoltaics. Organic semiconductors for future photovoltaics. Organic semiconductors based on photovoltaic devices are able to absorb light of different wavelengths and convert it into electricity or electrical signal. By converting the light into electricity, the organic solar cells represent a clean, cost-effective, and easy processing solution to address the energy crisis problems. By converting the photons of different energies into electrical signals, the organic photodetector shows the potential in the flexible, high sensitivity, and the high speed multicolor sending applications. For both photovoltaic devices, the crucial materials are the organic semiconductors, which are the major light harvester in the devices. As soon as the photons are observed, bounded electron hole pairs are formed in the organic semiconductors. By carefully adjusting the energy levels for each material, both the electron and hole can be collected on the cathode and the anode respectively to realize fully utilization of solar energy. Low bandgap polymeric semiconducting materials are of top interest where the low band gap ensures photons of lower energy being absorbed and thus exploiting the sun irradiation to near infrared. Moreover, the incident photon to current conversation at a different wavelength from ultraviolet in infrared also opens a door for organic photodetectors. By far, the spot has been focused on development of low band semiconducting polymers with controlled or minimized band gap, and there has been developed five effective device rules for approaching low band gap semiconducting polymers with advanced photoelectrical properties such as high molar absorptivity, suitable energy levels, high charge carrier malleability, and high solubility in organic solvents. The semiconducting properties of conjectured polymer are originated from the biconjected structure, where the pi electron has certain degree of delocalization. Thus, by turning the freedom of pi electrons, the delocalization and distribution of electrons in polymer system would be changed, which gives rise of different energy levels as well as energy band gap. From this angle, the idea of fused hydrocycles structure and groups and atoms bringing adjacent adjacent rings for maintaining a high planarity have been developed for facilitating by electron flowing along the polymer backbone and enhance the delocalization. In addition, strategies of introduction of electron withdrawing units for lowering energy levels, electron donor, electron acceptors units, copolymorphization for non-narrowing bandgap, and 2D conjugation for broadening absorption and enhanced hole malleability have also been developed. Low bandgap semiconducting polymers with facially dual energy levels exhibit high potential for releasing the multicolor photodetection with single polymers blended with fluorescence derivatives which circumvent the limited bands converted by inorganic material. Moreover, the low bandgap semiconducting polymers also enable the utilization of photons at a longer wavelength, which eventually give rise to higher photon electricity conversion efficiency for solar cells. New semiconductor metals for efficient organic photovoltaics. Unlike its inorganic counterparts, organic solar cell technology is a promising candidate for solar energy conversion due to its low cost, lightweight, and use in flexible devices. UE funded scientists successfully developed organic wide bandgap semiconductors compatible with roll-to-roll methods and excellent photovoltaic properties. High efficiency and low cost are crucial to ensuring wider adoption of solar cell technology. As of 2013, organic photovoltaic in efficiency and stability problems combined with the promise of low cost and increased efficiency made them a popular field in solar cell research. Wide bandgap organic semiconductors have high potential to fulfill expectations for high efficiencies. In particular, organic polymers with a wider bandgap than the commonly used inorganic silicon are highly desirable complementary absorption in tandem solar cells. Within ecosystem development of low bandgap conjuncted polymers by eco-friendly synthetic methodologies for high performance organic photovoltaics. Scientists successfully synthesized highly stable bandgap conjuncted polymers that hold great promise for industrial scale manufacturing of flexible large area devices. Thank you.